We will now move to stress formulation. In order to use stress formulation for determining stresses, strains, and displacements of a body, we have to start from a stress function, find out the relevant stresses. After that, we use the constitutive equation to find out the strains, and finally, from strains, we can work out the displacement. In the case of stress formulation, it is important that we ensure compatibility. So the displacement which will be got from the strain have to be compatible with the strains. In the stress formulation, we don't need to satisfy the equilibrium equation because the stress formulations used will automatically ensure equilibrium. This is in contrast to our previous displacement formulation, in which we started off from displacement and found the strains, and after that the stresses. In the displacement formulation, we had to ensure the equilibrium. However, the compatibility was already satisfied from the get-go because we started with the compatible displacements. So let us see how stress formulation works. As we said that in the case of stress formulation, we have to start from a stress function which will ensure equilibrium. One of the well-known stress function is Airy stress function. Airy stress function is a mathematical tool used in the field of elasticity to represent the stress field in two-dimensional isotropic elastic material. The Airy stress function is particularly useful for solving problems related to deformation of thin plates and bending of beams. One of the advantages of Airy stress function is that equilibrium is automatically satisfied, which means to say that plugging the stress function in the equilibrium equation, we will have the equilibrium equation satisfied. It is important to note that Airy stress function is out of many available stress functions. In order to solve our elasticity problem by using stress formulation and employing Airy stress function in particular, we have to set out a solution strategy. So there are three important points which must be ensured. The first point is that we start with a problem tailored from stress which satisfies equilibrium. So in other words, we take Airy stress function and from there onwards we find the value of stress, then strains, and finally displacements. Then the second strategy is to enforce compatibility to restrict this form. As we discussed that the solution won't be compatible, therefore we have to enforce compatibility. And once we enforce compatibility, then the displacement field is guaranteed to exist. So in a 2D elastic body, the stress field can be described by sigma 11, sigma 22, and sigma 12. The Airy stress function, denoted by phi, is introduced just to simplify the solution of stress equation. The stress components related to Airy stress function are shown over here. So sigma 11 is phi comma 22 plus omega underscore. Sigma 22 is equal to phi comma 11 plus omega. Sigma 12 is equal to minus phi comma 12. Please note that omega is a function of coordinate x1, x2, and this is called the potential function that delivers body force. It is important to note that the body force used in the Airy stress function is conservative body force. A conservative force is a concept related to the work done by a force on an object as it moves through displacement in a conservative force field. The important characteristic of a conservative force is that the work done by the force on an object is independent of the path taken by the object between 2 points in space. The conservative force is defined as the negative gradient of a scalar potential. Thus, if we have a vector field F and we try to move the body in that field by a differential displacement dr, then F dot dr is independent of path. For example, gravity field is a conservative field. So the work done by gravity on an object when the object is moved between any 2 points in space is independent of the path taken. The work done by gravity will only depend on the initial and the final position of the object and not on the specific trajectory it followed. Thus, F dot dr must be equal to 0. And this is equivalent to say that F dot dr is an exact differential. In the case of exact differential, if V is an exact differential, that would mean that a dV, which is a small part of V, is only dependent on the initial and final position of this function. In other words, we can write that dV is equal to partial V by partial x dx plus partial V by partial y dy plus partial V by partial z dz. Since gravity is a conservative field, therefore, so in our case, the omega will be equal to rho g x2, where rho g is gravity and x2 is the direction of gravity. So rho g is the weight of the structure and x2 is the direction of gravity. And now we will try to satisfy equilibrium. In the case of 2D isotropy earlier, we derived two equilibrium equations, which were sigma 11 comma 1 plus sigma 12 comma 2 plus x1 equal to 0 and sigma 21 comma 1 plus sigma 22 comma 2 plus x2 equal to 0, where x1 and x2 were body forces. Now we can plug the Airy stress function in these equations and make sure that the equilibrium equations are satisfied. So the Airy stress function sigma 11 is phi comma 22 plus omega and sigma 22 is equal to phi comma 11 plus omega. Sigma 12 is equal to minus phi comma 12. Those can be plugged in the equilibrium equation and we get phi comma 22 1 plus ohm comma 1 minus phi comma 122 minus ohm comma 1. The second equation is phi comma 121 plus phi comma 112 plus ohm comma 2 minus ohm 12 equal to 0. Let us now discuss compatibility. Before writing down the equation of compatibility, let us introduce ourselves with another operator called Laplacian operator. This operator is normally represented by inverted triangle square. It's defined as inverted triangle square of a quantity or a function is equal to twice derivative of that function with respect to x1 plus twice derivative of that function with x2. And normally it's written as delta dot delta times that quantity, and as a result it becomes 2. So rewriting our compatibility equation in terms of Laplacian, we derived compatibility equations previously, which was sigma 11 plus sigma 22 whole bracket comma 11 plus sigma 11 plus sigma 22 whole in bracket comma 22 equal to minus 1 by w x1 comma 1 plus x2 comma 2 whole in small bracket. So this term in its short form can be written as this one: inverted delta square sigma 11 plus sigma 22 In other words, Laplacian of sigma 1 1 plus sigma 2 2. As we said, Laplacian of this function is sigma 1 1 comma 1 1 sigma 2 2 comma 1 1 plus sigma 1 1 comma 2 2 plus sigma 2 2 comma 2 2. So that comes out to be the same what we had over here. Just reminding ourselves that this equation is for isotropic linear elastic material and equilibrium equation is satisfied. Now, plugging the Airy stress function, which we defined previously as sigma 11 equal to phi comma 22 plus ohm and sigma 22 equal to phi comma 11 plus ohms. Sigma 12 is equal to minus phi comma 12. Plugging that in the compatibility equation, and we get phi comma 22 plus ohm plus phi comma 11 plus ohm whole in small bracket plus 1 by w ohm comma 11 plus ohm comma 22 both in small bracket. So this one is Laplacian of ohm and this one is a Laplacian of phi plus 2 ohm. Now if we have already a Laplacian inside the bracket, that can be made delta 4 of the quantity. And the way that is done is inverted delta 4 phi can be written as inverted delta square phi. Now this delta square phi can be written as a capital phi. So inverted delta square capital phi is equal to capital phi comma 1 1 plus capital phi comma 2 2. Since capital phi is equal to inverted delta square small phi, so opening capital phi comma 1 1, that comes out to be small phi comma 1 1 plus small phi comma 2 2 all in small bracket comma 1 1. And similarly the second term comes out to be small phi comma 1 1 plus small phi comma 2 2 all in small bracket comma 2 2. These terms can be then added with each other. Thus, this is our compatibility equation. In order to understand what Laplacian is an operator which is shown or symbolized as inverted delta square. And this operator accepts a function and it gives out a function. Laplacian function, which is the double derivative of a function with respect to all the coordinates, actually gives us the direction we should go to increase our function most rapidly. So in other words, if we have got this function which is f of x, y, z, and we draw its gradient, which means that we draw vectors showing this slope of this curve, remembering that gradient is the slope of the steepest descent. So we would have in 2D plane bunch of vectors. Now, after that, if we take divergence of that vector field at a particular point, that will give us Laplacian. Divergence of a gradient vector which are facing each other is negative, and divergence of a valley will be positive. Please note that in the case of valley, we have vectors pointing outwardly. This is analogous to a 1D function where double derivative of a function, if greater than 0, is actually showing minima, and double derivative of function if less than 0 is showing maxima. So in short, the Laplacian tells us how much of a minimum point is corresponding to x, y, and z. So what is the maximum minima, or what is the absolute maximum minima? So that was a Laplacian. Now we have got our equilibrium done. We have addressed the compatibility equation. The final variable remaining is displacement. In the case of stress formulation, we have to ensure compatibility, and the compatibility equations are more than the unknown displacements. So therefore, it is quite challenging to get a unique displacement. If we find one, that will guarantee a unique displacement, but finding a displacement is challenging. So therefore, we use an iterative approach. We start with a particular displacement, plug that in the constitutive equation, see whether it works or not, and then we keep on changing it. So just to give one example, say we assume that we predict a displacement which looks like this. So 2 mu u1 is equal to minus phi comma 1, and 2 mu u2 is equal to minus phi comma 2. Now, how can we plug these displacements into constitutive equation? The answer is that we can write epsilon alpha beta in terms of u1, u2, and then from there we can plug the values of these ones. So we will get some value on the left hand side. In the case of right hand side, we can plug the Airy stress function and see whether the right hand side is equal to left hand side. That's the procedure for ensuring a unique displacement. Now, in this case of displacement field, we have got two problems. One is a minor problem, another one is a major problem. One problem is that the rotation matrix is 0. So the rotation matrix defined as omega 1, 2 is equal to half of u1, comma 2 minus u2, comma 1. Now, in the case of our previous presentations, we derived equations for shear strain, which look like these ones. Gamma 1, 3 is equal to u1, comma 3 plus u3, comma 1. Gamma 2, 3 is equal to u2, comma 3 plus u3, comma 2. And gamma 1, 2 is u1, comma 2 plus u2, comma 1. Since both terms of these equations are positive, that tells us that there is a shear deformation. But there can be a scenario where this box just show a rigid body rotation without inducing any strain. So in that case, we can say that if we put the second term as negative and take the mean of it, that rotation, that would be just like a rigid body rotation. So this displacement would be equal to u2 by x1, and this displacement will be equal to minus u1 by x2. So if one term is getting subtracted from the other term, that would give us a rigid body rotation. And that's what has been shown over here. We have half of u12 minus u21, which is a rigid body rotation, and that rotation matrix in this case comes out to be 0. And normally we should have a displacement field which should have rigid body rotations. So that is one problem, but that's not the main problem. The main problem is that if we plug the values in our constitutive equation, we won't be able to equate the left hand side with the right hand side, and that has been shown over here. So therefore, we have to change our selection of displacement field, and if we take something like this one, which is 2 mu u1 is equal to minus phi comma 1 plus omega psi comma 1 2, and 2 mu u2 is equal to minus phi comma 2 plus omega psi comma 1, where psi is a function whose Laplacian is 0, and psi 1 2 is equal to inverted delta square phi minus small bracket 1 by w minus 2 times O. It turns out that Laplacian of psi equal to psi capture shear stress, and psi 1 2 is equal to Laplacian of phi minus 1 by w minus 2 small bracket times O. This is just a displacement which is got arbitrarily. So let us plug some values in our constitutive equation and see whether it makes sense. In the case of shear, the axial stresses are zero, so this term will become zero. We will have only the shear stress remaining over here. Epsilon 1, 2 can be put as half u1, comma 2 plus u2, comma 1. Now putting values from this displacement field, we get a condition inverted delta square psi must be equal to 0. In this second case, we have introduced a new function c, and that c has to satisfy these two conditions. If it satisfies these two conditions, then we can use it as a new function in our proposal. Now let us briefly discuss what can be the options for phi. It is important to note that in the case of no body force, we would have delta 4 phi equal to 0. So ohm will be equal to 0 and delta square ohm will also be equal to 0. Thus the right hand side will become 0 and we would have inverted triangle 4 times phi must be equal to 0. We have got an option either to select phi as a polynomial function or a trigonometric function. If we opt for choosing a polynomial function, it is important that we put appropriate terms of polynomials, and each term must be of a sufficient degree to give us appropriate solution. Now, for example, if our polynomial function is linear, which is ax1 plus bx2 plus c, in this case, all our stresses comes out to be 0 and the compatibility is also 0. So this function will give us a trivial solution. Therefore, this function will not be appropriate for analyzing a structure. As we are dealing with a 2D space, therefore we have terms related to both the coordinate system. In the case of polynomial system, we use the so-called Pascal's triangle. So the Pascal triangle is shown over here. The first line shows a polynomial function of first degree. The second line shows polynomial function of a second degree, and so on and so forth. Now let us see what will happen if we take a quadratic polynomial function. In this case, we would take ax1 square plus bx1 x2 plus cx2 square equal to 0. Now in this case also, the compatibility equation is automatically satisfied. However, we can have a stress field which is uniform because we are getting our stress field in the form of constants. The solution got from a quadratic polynomial function can be the first approximation to the real solution. So the quadratic polynomial function has given us uniform stress field as shown in this figure. So if our x1, x2 plane is as in this figure, then all the stresses, shear as well as the axials, are of uniform magnitude. In the case of cubic polynomial function, again, the compatibility equation is satisfied. The stress field is varying linearly, as can be seen that the terms involve first degree of the variable. The cubic polynomial function can be used if we have got a cantilever deep beam. Similarly, in the case of quartic, we have all the variables of degree 4, and in this case we end up with a compatibility equation. The compatibility equation is not satisfied automatically, so we get some constants, and these constants summation must be equal to 0 in order to satisfy the compatibility.